Good evening, everyone. Welcome to live session 7 of the NPTEL course on mechanics of material. So, today we'll be discussing the concepts covered in week 7 lectures, and I'll be explaining you with some of the examples which will help you to do the assignment in week 7. So, let's start with the live session 7. So as usual, I will first summarize that what happened in the late of week 6 because it includes the beam bending equation and all, and what happened in the week 7 lectures. So first I'll give you the summary and then we'll start with the problem session. Okay. So today is 11th September. So I won't be deriving the equations which was derived in week 6 or week 7. Just I will give you the important formulations which will be requiring and will be helpful for you to solve the problems which will be dealing in this class. Okay. So beam. Okay. So suppose we have a beam like this. So I'll be doing for the general loading case, and the load has been applied like this. Okay. And our coordinate system is like this, as usual, x, y, and z. So loading is acting at y direction. So this is qy. The unit will be is load per unit length. This will be our L, height h, and width d. Okay, so we can represent this beam like this also. Suppose the beam is simply supported. We can draw with the help of a line also. So this support is known as hinge support. And this is roller support. And this is the loading, general loading. So what we got to know after deriving all the possible equations, that traction won't, if we cut a surface, that traction will vary along the length, along the width in magnitude as well as in direction. So after taking the traction in the EX direction, we got several formulations. I'll write the expressions. Okay. So we got like axial force P will be equal to area integral of sigma xx dAx. This is the axial force, first formula. Okay. Similarly, we got shear force acting in y direction, which will be again area integral of sigma xy dAx. And last, shear force acting in z direction is equal to sigma xz dAx. Okay. One second, I'll just check whether I started recording or not. Okay. So this is the shear force acting in y direction. This is also shear force acting along z direction, z. Okay. Then we have studied bending moment and torsional moment. So torsional moment T is given as area integral of sigma xc into y minus sigma xy into z over dAx. This is torsional moment. And bending moment along y and z direction is my is equal to sigma xx into z dAx, and bending moment along z direction is equal to negative of sigma xx into y dAx. This is bending moment along y direction. This is bending moment along z direction. Okay. Then we studied how to relate shear force and bending moment and loading. So this Qy loading is nothing but integration of sigma yy into dz. Okay, as it acts in the y direction and normal to it. Okay, now we study relations. In week 6 towards the end, and in the week 7 we have studied how to relate bending moment and shear force and the loading. So three basic relations has been given. What is d of vy by dx plus qy is equal to 0. For detailed derivation, you can go to the week 6 last parts and week 7 initial parts. Okay. Second, dmz by dx plus vy is equal to 0. mz is nothing but bending moment in z direction, vy is nothing but shear force in y direction, qy is loading applied along the y direction. Okay. And last, if we differentiate the equation 2 and put the values of 1, we'll get d2m z by dx square minus qy is equal to 0. These are the three important relationships which will help you to solve the example better. We'll see while solving the problem. Okay. Okay. Then we see how to find the centroid of the cross section and moment of inertia of the cross section. So centroid of the cross section is nothing but y centroid is equal to integral of y dAx upon dAx. Okay. And moment of inertia izz is nothing but integration of y minus y naught whole square dAx. Okay. This is how we calculate the centroid of the cross section and moment of inertia. Okay. Then we see the important thing which is known as beam bending equation. So before deriving the beam bending equation, we took certain assumptions which are plane sections remains plane. That is, there will be no change in angle between the coordinate system before and after bending. Okay, which implies no Poisson's effect will be encountered in this cases. The problem will be considered. Also, sigma xx will remain 0 at the plane section. Okay. Next, we say beam will be homogeneous. Beam is homogeneous, which means E will be constant, which again means E will be same or E is same in both tension and compression. Okay. So after considering all these assumptions, the equation finally we got is mz by izz is equal to negative sigma xx by y minus y naught equal to E into d2 del y by dx square. This is known as beam bending equation. Okay. Okay. Now then we studied two things. One is radius of curvature, which is nothing if we have something and we have to find at one point. Just draw a circle at that point and the radius for that circle will be known as radius of curvature. This is denoted by r, which is equal to 1 upon d2 del y by dx square. Okay. Next thing we study is curvature. Curvature is denoted by phi, which is equal to 1 upon. Okay, this is nothing but the angle of a strain curve, strain profile. One second. Here this is a strain, variation of strain. This angle is given by phi. Okay. So this is what is summary covered in week 7 lectures. I have not derived all the things. I have just given you the formula which I have required in solving the week 7 problems. Also, I will be giving you hands-on experience on those problems also. So these are the basic equations you need to understand and you need to remember while solving those equations. Okay. So now coming to the problem solving session. So problem 1. So first we'll read the problem, what the problem says. So as the problem says, a cantilever beam fixed at A and is 10 meter long is carrying a load which is acting downward and it's a distributed load as shown in figure. I'll show you the figure after reading the question. The load is acting in the principal plane of the cross section. If the wooden beam, the beam is made up of wooden, has a rectangular cross section, the cross section has been made is rectangular with depth by width ratio, h by b ratio has been given 2 and dimension of h is given which is 500 mm. So since h by b ratio is given and h is 500, we calculate b will be h by 2 which is 250 mm. Okay. Last it is said assume the Young's modulus of wood to be EW equal to 10 GPa, that is 10 into 10 to the power 9 Newton per meter square. Okay, ignore the self weight of the beam. So then you have to answer the following questions. Here what are the reactions at fixed and magnitude of the reaction, moment or location. We'll see one by one while solving the problem. So this is the diagram. So this is a cantilever beam. Okay. So following the coordinate axis as we follow usually. This is y, this is x and this is z. So loading is applied on the y direction. Cantilever beam, it is fixed at point A and it is free at point B. Okay. A uniformly varying load has been given which having a magnitude of 5 kilonewton per meter at point A and 10 kilonewton per meter magnitude at point B. Okay. So this is a uniformly varying load, UVL load. Okay. Okay. Now cross section has been given to us also. It's rectangle cross section. Okay. Which is having, write the coordinate axis y z. Okay. And dimension of h is given as h is equal to 500 mm given in the question. And this is b. H by b is given to us is equal to 2. So b will be equal to h by 2, which is equal to 500 by 2, which is equal to 250 mm. Okay. So width of the rectangular cross section will be equal to 250 mm. So this is the cross section given. Fine. Okay. Now first question they ask, what is the reaction at fixed end? Fixed end is point A. Okay. So first we'll draw the free body diagram. Okay. First part. So I remove the support conditions. I will put the loading. This is the loading given to us. Here 10 kilonewton per meter. You can see it's a shape of trapezoidal. Okay. Okay. And this reaction RA will be acting at point A. Okay. According to the free body diagram. This is A. This is B. Okay. So if I take the vertical equilibrium, so I will take the vertical equilibrium sigma Fy is equal to 0, which implies Ra minus, what is the equivalent load acting? Is nothing but the area. Okay. What is this? Half. What is the area of the trapezoid? Half into sum of parallel sides, which is nothing but 5 plus 10. Okay. Into length. Length given to us in the question is 10 meter. Okay. Length in the question is given as 10 meter. Okay. So area of trapezoid is nothing but half into base. Base is nothing but length, that is 10, into sum of parallel sides. Here parallel sides are this 5 kilonewton per meter and 10 kilonewton per meter. This is what written here, 5 and 10. This 10 is nothing but length. Okay. Which is equal to 0. So Ra will be equal to half into 15 into 10, which is nothing but 75 kilonewton. This is the reaction at A, at fixed end. Okay. We'll write here answer one by one. So Ra is equal to 75 kilonewton. Okay, first part done. Second part. Magnitude of reaction moment at fixed end. Okay. Magnitude of reaction moment at fixed end. Okay. See, if a support is fixed, it offers a resistance in the upward movement as well as in the moment. Okay. In beam, we ignore the axial force. Okay. So since in the fixed end, moment will also be there. We'll balance the moment with the help of moment equilibrium. Okay. So suppose I will make a free body diagram here. So in trapezoidal, equivalent load acting is 75 kilonewton RA 75 kilonewton. Moment is applied like this, suppose MA here. Okay. What is the resistance X will be? See, 75 we have calculated with the help of half of base into sum of parallel sides. This is the equivalent load acting on the beam. Okay. This X will be the CG. So CG of trapezoid will be what is the CG? It's nothing but 1 by 3 into length L, which is nothing but B, base. Here base is equal to 10 meter. Okay. Into twice into opposite side. Since we are calculating from the left to right, from fixed end to free end, so opposite side will be equal to 10 kilonewton per meter plus near side upon total of both sides. Okay. So CG will be equal to 1 by 3. B is 10 meter into 2 into opposite side is 10 plus 5. Sum will be equal to 15. 10 plus 5. This will come out to be 10 by 3 into 25 by 15. So CG will be equal to 50 by 9. Okay. So this CG will be nothing but X. This will be equal to 50 by 9. So now we'll balance the moment. Okay. We'll take clockwise moment as positive here and balance the moment equilibrium at A point. What we will get? 75 into 50 by 9 minus MA is equal to 0. This is A point, this is B point. So MA we will get as 1250 by 3 unit kilonewton meter. So since MA came out to be positive, so the assumed direction what we have assumed is correct. That is the anti-clockwise direction. So reaction moment at fixed end, that is MA, is equal to 1250 by 3 kilonewton meter. Okay. Okay. We'll write this answer as well. So MA we got as 1250 by 3 kilonewton meter. Okay. Now there is a location of maximum bending moment. See, there is a difference between the second question and third question. Second question says reaction moment. Okay. It is called as reaction. The action we provide is bending moment. Okay. So if a loading is applied in the vertical y direction, the bending moment will arise in the z direction. So first we have to calculate the expression of bending moment, and then we have to see whether where the maximum bending moment is coming. Okay. So third part. Location of maximum bending moment. Okay. So now before getting to the first I'll tell you. So what expression we'll use to get the bending moment equation first? So as I have told you earlier in this class at the very starting, d2 mg by dx square is nothing but equal to the loading applied to the beam. Okay. Now qy is not given directly because qy is uniformly varying load, UVL. with 5 kilonewton per meter magnitude applied at A, that is fixed point, and 10 kilonewton per meter applied at B point. So first we have to find the expression of Qy. So Qy is nothing but 0.5 x plus 5, where x lies from 0 to 10. See, x is our length. So length is 10 meter. So x will vary from 0 to 10, where 0 x equal to 0 tells us fixed point, and x equal to 10, that is point A, free point, which is point B. Okay. So you can check with this expression. When I will put x equal to 0, we'll get 5 at x equal to 0, and if I will put x equal to 10, I will get 10 when x is equal to 10. Okay, which is there? We have, and it's a linearly varying from point A to point B. Okay, so Qy will be 5 at x equal to 0, and Qy will be able to tell 10 when x equal to 10, which is at point B. So hence the expression of Qy will be equal to like this. Okay, how to derive this expression? I'll show you. This is the loading given to us, and this is 10 meter. So what is the slope I will get for this line? This theta, it's nothing but this height, which is equal to 5 kilonewton per meter, by length 5 by 10, is equal to 0.5. So 0.5 is our m. Sorry. Slope of this line is 0.5. Initial intercept c value I got is 5. So equation of straight line is mx plus c. So our y is nothing but loading. Our m is nothing but 0.5, which is varying with x, plus intercept is 5. And x varies from 0 to 10. This is how I got my loading expression. Okay. So once you got the loading expression, just put into the formulation. What is the formula? d2mc by dx square is nothing but equal to qy, which is now is equal to 0.5x plus 5. Okay, where x varies from 0 to 10. This is the expression. Now integrating, I write this expression as 1. Integrating equation 1 twice to get mz. Okay. So when we integrate this expression twice, what we'll get? We'll get mz will be equal to 0.5x cube by 6 plus 5x square by 2 plus c1x plus c2. This is expression 2. Now we have to put boundary conditions. Okay. See, why we need boundary conditions? Because we have two unknowns, C1 and C2. C1 and C2 are two unknowns. Okay. So we need at least two equations to get C1 and C2. So what we know? Just now we calculated reaction moment at fixed end. We know mz at x equal to 0 is nothing but 1250 by 3 kilonewton meter. Okay. And second, what we know? mz at x equal to 10 is equal to 0. Moment at free end will always be 0. Okay. bending moment at free end will always be 0. Okay. Similarly, shear force also. Shear force at free end will always be 0. This we need at later parts. Okay, but I have written here only. Okay, try to understand each and every point because these are the basics that you are gaining. From these basics, you will be solving the typical problems also. But the foundation is this only. So try to learn each and every step. And if you have any doubt at any part, you can always ping me. Okay, I'm always there to help you. Okay. Now moving to the questions. Now we have two boundary conditions, mg at x equal to 0 that we have derived in the previous part. This is okay. 1250 by 3 kilonewton meter and mg at x equal to 10 is equal to 0 at the free end. So now putting these two equations, putting one first in equation 2, what we will get? Put x equal to 0, we got C2 is equal to 1250 by 3. Okay. And if we putting second in equation 2, what we will get? We'll put 10 here. Okay. So 0 equal to 0.5 into 10 cube by 6 plus 5 into 10 square by 2 plus C1 into 10 plus 1250 by 3. By solving this thing, we'll get C1 equal to minus 75. Okay. So after putting these two boundary conditions, we got C1 and C2 and finally we got the expression of our mg as 0.5 x cube by 6 plus 5x square by 2 minus 75x plus 1250 by 3. This is the expression of mg. This is write as equation 3. Okay, remember this expression because this expression will be needing in later parts of this question to solve. Okay, so what is asked in the question actually? What is the location of the maximum bending moment? Okay, where it is? See, here it is asked. Location of maximum bending moment. So we have found the bending moment equation. To find the maximum of some value, what we do? We just derive that expression and put it to 0. And wherever the location is, we'll put the location will be termed as maximum location. And value corresponding to that location will be termed as maximum value. Okay. So for maximum for location of maximum value, what we'll do? We'll just derive dmg by dx and put it to equal to 0. Okay, this is the standard thing. But this example, this question has something else. I'll show you. So when we do this dmg by dx, what you will get? 0.5x square by 3 plus 5x minus 75 equal to 0. Okay. This is the quadratic equation. Okay. And to find the roots, as per the quadratic formula, we know that b square minus 4ac should be greater than 0. But when you calculate this b square minus 4ac here, what you will get? This is the standard quadratic equation. So where you want this thing to be greater than 0 for getting the real roots. For getting real roots. But here if you put b square is nothing but 5 square minus 4 into 0.5 by 3 into minus 75. Okay. Yeah. So what you will get? So you will get as 25 minus 2 plus 150 by 3. One second. 250. 75. Okay. So these are the real roots. Okay. But if you find the roots of this equation, it will come out to be x greater than 10. Okay. But or it will come x less than 0. Okay. Or okay. Okay. See, I'll show you. So I'll just find out the roots also for you. Don't go for this. So how to find the roots of the quadratic equation? Roots are equal to minus b plus minus under root of b square minus 4ac by 2a. This is how we find the roots as per the quadratic formula. So it's 5 plus minus under root of 75 by 2 into 0.5 by 3. Okay, we rewrite this thing. It's equal to minus 15 plus minus 3 under root 75. Okay, so this is the expression of the quadratic formula, that how you will find roots. Okay. Okay. So you can see this, that this will not come in the range of 0 to x 10. Okay. Okay. See, minus 15 plus, if I open up the root of 75, it will be nothing but 8.660254. So root 1 will be having the value of minus 15 minus, if I multiply, it will be 25.9807, and root 2 will be having the value of minus 15 plus 25 point. So it is less than 0 and it is greater than 10. So both the roots do not lie in the range of our domain, that is x 0 to 10. Okay. Okay. So what will be the maximum value then? Location of maximum value. So then what you have to do if such cases arises, you just need to draw the curve of this diagram. So I'll tell you the shortcut. For cantilever beam, maximum moment will be at the fixed end. Okay. Okay. So this will be the case for cantilever beam. Okay. And if you draw the curve for this equation 3, you will see the curve for this equation if I plot in x and y direction, this thing. So curve will be nothing but a monotonic increasing function. Okay, decreasing function, sorry. It will be like this. I'll draw with different pen. This function will be like this if you draw the curve. Okay, so what you will see, this value is the maximum value, which is nothing but at the fixed end, 0. Okay, okay, got it. So the answer for our question is the location of maximum value of bending moment is at 0 meter, x equal to 0 meter. 1 second. Okay, so this is the answer to our third part. And this will always hold true for cantilever beams. The maximum bending moment you will get at fixed end. Okay, next is the magnitude of maximum bending moment. So what will be the magnitude? Fourth part. So mg expression I'll just take from here, equation 3. This is the mg expression we got. So maximum bending moment will occur at fixed end. Always for cantilever beam. Okay, which implies x will be equal to 0. Then mg max at x equal to 0 is nothing but 0 plus 0 minus 0 plus 1250 by 3. So mg max will be equal to at x equal to 0 will be equal to 1250 by 3 kilonewton meter. This is the maximum bending moment you will get. Okay, so this is the answer to your fourth part. I hope till now you got like what I was trying to explain you. Okay, so coming to the next part, magnitude of maximum bending normal stress. Okay, so fifth part. So as we know from our beam bending equation, what is that? mg by izz is equal to minus of sigma xx by y minus y naught. Okay, here since it's acting at the principal plane of the cross section as mentioned in the question, y naught will be equal to 0. Okay, so sigma xx, since magnitude has been asked, will be equal to mz into y by izz. Okay, this is there, but what we want maximum. So maximum sigma xx will be nothing but maximum of this and maximum of y. Okay, okay, so what cross section we have in our question? Rectangular cross section, where h is nothing but equal to 500 mm, b is nothing but 250 mm. This is given to us, and what is given to us? H by b equal to 2, and from that we found out b. Okay, so this is a CG of rectangle. Okay, suppose we The coordinate axis we follow is this. Okay. So as you have seen in the lectures, what is the variation of bending normal stress? It's nothing but like this. For rectangular cross section, you can go back to the lecture and see how it is derived. I won't derive because of the time shortage. So extreme normal bending normal stress will occur at extreme ends. This is the CG. From CG it's acting. What is the distance from CG? I will draw a different diagram with different solid color. So what is the distance of y? Y will be equal to h by 2, because maximum, this is nothing but sigma xx maximum. Okay, mod I will say in terms of magnitude. Okay, so for maximum sigma xx, y max will be equal to h by 2. And in previous part we see what is mg max. It is nothing but 1250 by 3, acting at fixed end. Just we saw in the last part while solving the problem. So after putting all the values, sigma xx max will be equal to 1250 by 3 into y max. Y max is nothing but h by 2. H by 2, h is given as 500 mm by 2. Since it's in mm, I will convert it into meter, which is equal to 10 to the power minus 3 divided by IZZ. So IZZ, we'll find out IZZ also for rectangular section. So IZZ for rectangular is nothing but BH cube by 12 from center of gravity. B is nothing but 250 mm into 10 to the power minus 3 to convert it in meter. H is 500 into 10 to the power minus 3 to convert it in meter, whole to the power cube by 12. Okay, so I will put this expression here. So after calculation all these three, sigma xx max I will get as 40,000 kilonewton per meter square, which is nothing but 40 MPa. What is MPa? 1 MPa is nothing but equal to 10 to the power 6 Newton per meter square, or 10 to the power 3 kilonewton per meter square. Okay, remember all these conversions, because in assignments the units have been given and you have to provide the answers in terms of those units. Okay, so getting the knowledge of units is very important, and to know the conversion. So we got sigma xx max as 40 MPa. So this is how fifth part will be solved. Okay, now coming to the sixth part. Sixth part, what you said, find the maximum shear stress. Fifth part, what was asked? They asked find the maximum bending normal stress. Sixth part, they have asked maximum shear stress. Okay, so maximum shear stress. Okay, so in the lectures you have seen how to find the maximum shear stress. It is given by the expression sigma xy is nothing but Vy by Izz into B. Okay, width on which it is acting, into Ys into As, where Ys is the CG of the shaded portion and As is the area of the shaded portion. CG means center of gravity. Okay. So now what cross section we have been given in the question? Rectangular cross section. Okay. This is the CG of rectangular. We are following this coordinate axis as I have told you earlier, y and z. So we have to find maximum shear stress. First we'll find out the expression of xy and then we'll maximize that expression by derivating and equating to 0. Okay. So how to find this expression? Suppose I have made this cut here and this is my shaded portion. Okay. This width is b given. I will just now write in notations. Finally we'll put the values. Okay. The distance from CG to the shaded portion is this y. Okay. So what is ys here? Ys will be nothing but, what is this distance? This distance will be equal to h by 2 minus y, because CG is at h by 2. Okay. So what is ys? Ys nothing but CG of shaded portion. So this is y, this plus this value, which is nothing but half of the height of the shaded portion. So after calculating, this will come as h by 4 plus y by 2. Okay. Okay. Now, what is sigma xy? Just now we wrote the formula. It is v into yas into as, vy upon izz into b. Now we have calculated ys. Ys is nothing but h by 4 plus y by 2. What is as? As nothing but this into this rectangular section is there, width into height. Okay. So it is nothing but h by 2 minus y into b. Okay. Now this b will cancel out b. What we will left? So after cut, final expression we will get is 6vy by bh. After opening izz also, izz is nothing but bh cube by 12. Okay, we'll get 1 by 4 minus y by h whole square. This is the expression we will get. Okay, this same expression sir has derived in the week lecture also, but for the sake of completeness I have also derived it for the rectangular cross section. So now what we are finding? We are finding maximum shear stress. So for that we have to find the expression of sigma xy. So this is the expression. Suppose this is equation 4. 1 second. This is equation 4. To maximize equation 4, what to do? To get maximum of sigma xy, what you will do? Differentiate equation 4 and equate it to 0. So when you will differentiate d sigma xy by dy, what you will get? 6vy by bh into minus of 2 into y by h, which is equal to 0. So it implies y is equal to 0 for sigma xy maximum. Okay. So what is the expression you will get after putting y equal to 0? Sigma xy max at y equal to 0 will be equal to 3 by 2 vy by bh. This is the expression you will get. Okay. Now for maximum you need vy to be maximum also. Vy is nothing but reaction at reaction on the beam. So in the very first part, we have solved the reaction of the beam. See, I'll show you. This is the reaction of the beam we got in the very first part, Vy value. So Vy is maximum only at fixed end. So the value is nothing but 75. Okay. I will also show you with the help of moment equation this thing so that you won't get confused. Okay. See. This is the equation of moment we got, bending moment. Okay. So we know the equation that dmz by dx plus vy is equal to 0. So differentiating the mz, what we'll get? 0.5 x square by 2 plus 5x minus 75. Okay. Plus vy is equal to 0. So vy is nothing but 75 minus 0.5 x square by 2 minus 5x, where x belongs to 0 to 10. So Vy max, if you see for this range, as I've told you, this is a decreasing function. So maximum value you will get is 75. Okay, which is at x equal to 0. Okay, since the curve is a decreasing function, okay, so now putting the value of Vy in equation 5, so sigma xy max you will get as 75, sorry, 3 by 2 into 75 by b. B is nothing but 0.25 meter into h 0.5 meter. It is, if I solve, we will get as 900 kilonewton per meter square. This is nothing but 0.9 MPa. Okay. So Arnav, you joined late. We are solving one question, okay, which is given in the assignment also with different twist. Okay. So I'll recap you so that you also will be in the same page. Okay. 1 second. So suppose we have the question like this. Okay. This is a cantilever beam fixed at point A and free at point B. Okay. Our coordinate axis system we are following like this. Okay. X, Y, and Z. Okay. The load is applied is a uniformly varying load. Okay. It is uniformly varying at all the parts along the length. Okay. With having 5 kilonewton per meter load at point A and 10 kilonewton per meter load at point B. Okay. And we have given a cross section, rectangular cross section, having h 500 millimeter given in the question, and h by b ratio is also given in the question 2. So since height is given, we will find b with the help of this ratio, which is nothing but h by 2 for our case, which will be equal to 250 mm. Got it? Since h is 500 mm given, so h by 2 is 250 mm. Okay. So now first question was the reaction. First question was reaction at fixed end. So when you have uniformly distributed load, how you will find reaction? You will just multiply the load with the length. That's what you will do.
Yes, sir.
So here in uniformly varying load, this is nothing but uniformly varying load.
Sir,
Yeah.
ये जो आप FY निकाल रहे हैं, ये मतलब असाइनमेंट में क्वेश्चन दिया था, द मैग्नीट्यूड ऑफ Y कंपोनेंट ऑफ अ रिएक्शन फोर्स FY
Both are
एक्टिंग
same.
ऑन अ फिक्स्ड इन A, मतलब यही है ना?
Yeah, same. Yeah.
ओके
But there the loading is
ये
opposite,
मतलब
other way around. 10 is applied at A, 5 is
Okay,
applied
sir.
at B. So try to understand the
Yes,
question,
sir.
then for solve the assignment. Okay.
Okay, sir.
So since this is uniformly varying load, you can see the shape is like trapezoidal. So if we do the free body diagram, at A point reaction will be applied like this. At B point no reaction will be applied because it's a free end, and load is applied like this. Okay. So if I go with force equilibrium at y direction, we'll get is Ra minus area of loading. Area of trapezoid is nothing but half into sum of parallel sides. What are parallel sides? 5 and 10. Okay, sum of parallel sides into length, which is 10. Okay,
Okay, sir.
that is how you will get Ra. Okay, magnitude of reaction moment. Second question. You know this 75 kilonewton is applied with the help of area of trapezoid, which is nothing but half into length L, which is 10. Why I wrote B? Because it is base basically into sum of parallel sides. Okay, if you calculate, it will come out to be 75, and it will act as a CG. CG is center of gravity of trapezoid. What is the center of gravity of trapezoid? Is nothing but 1 by 3 into base into 2 into opposite side. So you are calculating from A. So opposite side will be B. So 2 into opposite side plus near side upon total of both sides. Okay. So then you will get CGS 50.9, 50 by 9, and then you balance the moment equilibrium, and you will get the moment. Okay.
Okay, sir. Yes, sir.
Then similarly, we'll be finding all the other parts. You can, after this lecture, you can go back with this lecture and find all the parts one by one.
Yes.
I have explained in a detailed manner.
Yes,
Okay. So I just
Okay,
complete this
sir.
question. Okay. So you understood the question, what we are solving. Okay. So just follow the other parts, last parts, because last parts are independent of the parts that I have solved so far. Okay. So now we are in the seventh part, I guess. Yes. So what is the seventh part in the question asks? Seventh part tells us location of maximum deflection. Okay.
Yes, sir.
So seventh is, well, 1 second, I'll add the page. Okay. So seventh part is location of maximum deflection. Okay. So I've told you initially in the class that the formula for finding the location, finding the expression of deflection first, because first we find the deflection expression, then we'll find the maximum. Okay. So as per the beam bending equation, d delta y by dx square is equal to mz by EIZZ. Okay.
Yes, sir.
I show you the formula of beam bending first. This is the beam bending formula. Okay. So this d2 del y by dxy is nothing but put E underneath this. So it's equal to mz by EIZZ. Okay. Fine. So this is the formula. So we know the expression of mz. We have derived. This is the expression of mz. Okay. So putting the expression of mz and integrating twice. We will find del y. Okay. So delta y, d2y first, we'll do this thing. It's nothing but I will write the expression first. E is easy. 0.5 x cube by 6 plus 5x square by 2 minus 75x plus 1250 by 3. This is the expression of mz we got in the by solving the previous parts. So now double integration will do. So delta y will become, you know the integration, no?
Yes,
all
sir.
these things. So if you will double integrate this expression, what you will get? I'll write 0.5 x5 by 120 plus 5x4 by 24. Okay, minus 75 x cube by 6 plus 1250 x square by 6 plus c1x plus c2. This expression you will get.
Okay, yes, sir.
Now we have c1 and c2 unknown.
Yes, sir.
So we need two boundary condition. Okay. Condition are required. Okay. So what are the boundary condition we have? It's a cantilever beam. So deflection at x equal to 0, fixed end will be 0. Also
X is
d delta y by dx, that is slope at fixed end, is always 0. Okay.
okay.
See, I'll tell you something which you have to remember always. These are truth. Deflection and slope are 0 at fixed support. Okay.
Okay, sir.
Bending moment and shear force, SF, I will write short form. Okay. 0 at free end. Okay.
Bending moment and shear force.
Free end.
Okay, sir.
0 at, sorry, both. Okay. And bending moment alone, not shear force. Okay. 0 at hinge support, bending moment and deflection, I will write. Okay.
Okay, sir.
Support and roller support. This you have to use everywhere while writing the boundary conditions. These are the boundary conditions. Okay. So here for fixed thing, deflection will be 0 and slope will be 0. This thing will come because we have a fixed support. Okay. So deflection and slope will be 0 at fixed support where, so the value of x will be 0. So after putting in delta y x equal to 0, what we will get? We'll get from this c2 equal to 0. Okay. And after derivating the sixth expression, you will get c1 equal to 0 after derivating. I won't derive, you derive and check it. Okay. So finally, what is the expression of delta y we will get? We will get 1 by e is easy 0.5 x5 by 120 plus 5x4 by 24 minus 75 x cube by 6 plus 1250 x square by 6. Okay. This is the expression of deflection we got. Okay. Seventh question. Okay. So they in the question what is asked? Find the location of maximum deflection. Okay. So for cantilever beam, maximum deflection will occur always at free end. Okay, remember this thing. Okay. So location will be x is equal to 10. Okay. This is the answer to our seventh part. Okay.
Okay, sir.
Now they say magnitude. So now we know the location at x equal to 10, we will get maximum deflection. So just put x equal to 10 meter in equation 7 to get del y maximum. Okay. So del y maximum at x equal to 10, what we will get? EIZZ 0.5 into 10 to the power 5 by 120 plus 5 into 10 to the power 4 by 24 minus 75 into 10 to the power cube by 6 plus 1250 to 10 square by 6. Okay. So this, by putting the value we got this expression. So what is E? E is nothing but 10 GPa given. This is nothing but 10 into 10 to the power 6 kilonewton per meter square. Okay. 1 GPa is 10 to the power 9 Newton per meter square. Okay. So this is how we convert. EIZZ is BH cube by 12. Okay. Where B is 0.25 meter, H is 0.5 meter, cube by 12. So EIZZ together will be, you can solve. Okay, it will come out to be 26041.6667 meter. Sorry. Kilonewton meter square. Okay. This value will come. Okay. You can check and solve. So delta y max after putting the value of EIZZ at x equal to 10, that is free end, will come out to be 0.416 meter. See, the important part is not the value. The important part is where it will lie. So maximum deflection will occur at free end. Zero deflection will occur at fixed end for a cantilever beam. Similarly, slope will be zero at fixed end. Bending moment will be zero at free end. Shear force will be zero at free end for cantilever beam. Okay, and in general also. Okay. So point is this: wherever our question has been asked, you should know all these things. So just follow these points. Okay, these are very important points. You should know all these things. Okay. Also, I have told in every part while solving that what is zero, what is not. So when you will go back, you will understand. Okay. So we have found what is delta y max, which is our eighth part. Delta y max equal to 0.416 meter. Next part is rotation at fixed end and rotation at free end. Just now I told you what is the rotation at fixed end. theta A fixed 0. Okay. And what is the rotation at free end? Free end, what is the value of x? Is 10. So what we'll do? We'll just derivate deflection to get rotation. So after this thing and putting the value of x equal to 10, we'll get what we'll get. I'll solve this thing. Okay.
सर रोटेशन और फ्री एंड जो आप जीरो लिखे हैं ये हमेशा रहेगा
Fixed end, not free end. I write here also. 9 part. It is always true.
ओके
Rotation at free end is equal to 0 radian. Always true.
ओके
Okay, 10th part. Rotation at free end. Sorry, above I write free is fixed end, not free end. Fixed end. Rotation at free end is equal to first derivative of delta, which is deflection, at x equal to 10. Because free end is located at x equal to 10 meter. Okay. So what is d delta y by dx? It's nothing but 0.5x4 by 24. Okay, plus 5x cube by 6 minus 75x square by 2 plus 1250 by 3x 1 by izz. So d delta y by dx at x equal to 10, which will be equal to theta a free end, will be equal to 1 upon EIZZ we just calculated, which is nothing but 2641.667. You put here 10 to the power 4 by 24 plus 5 into 10 to the power 3 by 6. Okay, after getting solving this, you will get theta at free end to be 0.056 radian. Okay. So this is the answer.
डिग्री में जो पूछेगा वो रेडियन में आया है उसी को डिग्री
No,
निकाल देंगे
no. Degree means C. 40. I'll tell you. 1 degree. I'll write in different colors. 1 degree is equal to pi by 180 radian. Okay. So 1 radian will be equal to 180 by pi degree. Got it?
Okay.
Just convert. So this is in radian. So just 180 by pi into 0.056 is in degree. Okay. Got it? So the answer will be 0.056 radian. So this is the first problem solved, all the parts, 10 parts.
Okay, sir.
Okay. So now we'll move into the second part. So second problem says the build-up steel beam having I-shaped cross section. Okay, this is in I-shape. First problem we have rectangular cross section. With flange width 500 mm and thickness 20 mm and web depth 1000 mm and thickness 10 mm is subjected to uniform vertical shear of 2 kN. Here they have already said that vertical shear of 2 kN has been given, Vy. So assume that both the top and bottom flange are of same dimension. So it's a symmetric I section, okay? Knowing that the I section is built up by welding the web with the flanges shown in figure, find the shear stress that the weld used to withstand. That should withstand. I'll draw the first figure. Okay. So this is the 1 second. So this is the I section given to us. Okay. So they have given TF, thickness of flange as 20 mm. Okay.
Yes, sir.
Thickness of web as 10 mm. Okay. Width of flanges. One second. What is the width of flanges? 500 mm. And height 1000 mm. Okay. H.
Yes, sir.
Top and bottom flange are of same size. Okay. So this is the question, and they have said that they have welded like this thing. This thing they have welded. This is the weld. So if you have seen the lecture, if this is the type of I section and this is weld, which shear stress will govern? Tau x, tau y will govern the weld design. Okay. Proper expression has been provided in the lecture of week 7. Okay.
Okay, sir.
So what is tau xy? With the help of formula is nothing but Vy by Izz into B into Ys As. Okay. Now in question, Vy equal to 2000 Newton given. Okay. Vertical shear. Okay. They have said we have to find a weld, whether the weld is given is will withstand the load or not. Okay, this shear. So weld is where the weld is present here. So the weld is present here in the this thing. Flange and width. You are getting it. The weld is provided here to lock this area, web and flange area. Okay.
Sir, height कितना दिया है? 1000
mm. So the weld is provided to lock the flange and the web area. So this V will be nothing but TW. Okay. The area, the interface where it access TW, which is nothing but 10 mm given. Okay. Now what is YS and AS? Since we have to find for the weld, so suppose this is the CG of I section. Okay. So this will be the shaded area. So we have to find AS and YS for this thing. Okay. This shaded area. Got it? So what is the CG of I section? Since it's a symmetrical section, and if I take my coordinate axis from here, from bottom, x, y, and z, so YCG will be at h by 2 plus TF. This will be YCG.
Yes, sir.
H by 2 plus TF, and XCG will be BF by 2. Okay. This. Okay. Understood? Okay. So we have to find for this section. Okay, this section. So this is Y. Okay, what is Y? Y will be equal to H by 2. So we have to find Y for H by 2. Okay. What is AS in this problem? Area of the shaded portion. So shaded portion is nothing but the flange. So it is rectangle. So area will be BF into TF. Understood?
Area of shaded. Yes, sir.
And what is YS? Y is nothing but distance from this CG. This CG to the CG of this rectangle. Okay. So
Yes, sir.
suppose CG lies here. So the distance between these two is YS. So it's nothing but H by 2 plus TF by 2. Because CG of this CG will be the CG of rectangle, which is nothing but half of height TF.
Yes, yes, sir.
So YS will be H by 2 plus TF by 2. Okay. So now what we know? We know this value, we know this value, we know this value. We know B. Now we have to calculate IZZ. Okay.
Okay, sir.
So IZZ in class, sir have told the generic formula. I'll just write. For detail, you can go back to class. Okay. To see. TW into H cube by 12 plus 2 into BF TF cube by 12 plus BF into TF H by 2 plus TF by 2 whole square. Okay, this is the formula for calculating IZZ of I section. Okay. Now I'll just put the formula here. TW is 10, H is 1000 cube by 12 plus 2 into BF is 500, TF is 20 cube by 12 plus 500 into 20, H by 2 is 500 plus TF by 2 is 10 whole square. Okay. So after calculating this, what we'll get is 0.60636 into 10 to the power 10 mm to the power 4 because all things are in mm. Okay.
सर ये BF 500 कहाँ से आ गया?
It's given in the question 500. This. Okay. Got
Sir,
it?
thickness 2. Yes, sir.
TF is 20. Okay. And TW is 10. So by putting all these things in the formula, we'll get IZZ as 0.6036 into 10 to the power 10 mm4. Okay.
Okay, sir.
So now we got all the things for tau xy. So just we'll put the value of all the things. So tau xy is nothing but Vy Ys into As upon IZZ into TW. Okay. So Vs is 2 kilonewton, which is 2 into 1000 Newton. Okay. Ys is H by 2 plus TF by 2, which is nothing but 500 plus 10, 510 mm. Okay.
Okay, sir.
So 510 AS is BF into TF. BF is 500, TF is 20. Okay. IZZ is 0.6036 into 10 to the power 10
Okay.
and TW is 10. Okay. So finally you will get tau xy as 0.1689 Newton per mm square, which is nothing but 0.1689 MPa, because 1 MPa is equal to 1 Newton per mm square. Okay.
Okay.
So this is the answer. So understood how to solve this problem?
Okay, sir. Yes, sir.
So this is these two problems are there which will help you or guide you to solve the assignment for the week 7 lectures. I hope I have covered all the topics. Okay. For any doubt you can ping me. Okay.
Okay, sir.
Okay, so we'll end today's class. Thank you for joining.